You're listening to Coding Blocks, episode 88. Subscribe to us and leave us a review on iTunes, Stitcher, and more using your favorite podcast app.
And check us out at codingblocks.net where you can find show notes, examples, discussion, and a whole lot more.
No, it's check us out.
Check us out.
Send your feedback, questions, and rants to comments at codingblocks.net. Follow us on Twitter at codingblocks, or head to www.codingblocks.net and find all our social links there at the top of the page. With that, I'm Alan Underwood.
I'm Michael Outlaw.
And I'm Jerzak.
Excellent. All right. And we always like to start off with a big thank you to people that have taken the time to go leave us a review up on the various places where it's done. So, Mike, do you want to kick us off?
Yep. From iTunes, we have Lego Parsons, Dennis Adolfi, Jerbaka, PS2178, and Tech Systems.
All right. Stitcher, big thanks to Chocolate IT and Timmy Nicepen.
That's an excellent name. And I meant to give a quick plug here last episode and totally forgot. So Mike Robbins, who does just crazy amounts of PowerShell stuff and writes a blog. We've talked about him before. You know, if you haven't, go check him out. But what's really cool is he and a couple other guys have teamed up and created a PowerShell conference book where they've got a ton of tips and tricks and things you can do. And we'll have a link on the show notes page here to where you can actually go buy that book, and all the proceeds go towards an on-ramp scholarship program. The authors get nothing. So, you know, if you want to get something that's really useful for you in your day-to-day and you do some things with PowerShell, and if you haven't done PowerShell, it's really cool. Go check this out, man. It's a good way to give back to, you know, a good cause and at the same time get something useful.
And finally, a big personal thanks to Jack and Crittner for rescuing me from my family vacation. So I got to do lunch over there in Baltimore, and I'm still dreaming about that Maryland cupcake. So thank you very much.
Very nice.
All right. Well, with that, let's get into the topic of our show tonight, algorithmic complexity.
And algorithmic complexity, we've referenced it a few times, especially recently talking about the Imposter's Handbook, and we're still kind of using that for some guideposts here. But algorithmic complexity is the study of how well algorithms scale in terms of time and memory.
Or space, right? Space.
Well, that'd be space.
Space.
Yeah, memory, space. That's what I mean.
Got it.
Yep, and it can be used to compare different algorithms. So if you've got two different algorithms, and you want to know like which one's faster, which one takes up more space, and that's a way to do it. And it also helps you get predictions. So like if you know something's performing now, and you think about doubling your input size or doubling your number of users or orders in a day, then you could do a little bit of napkin math and figure out what that's going to perform like, and see if you're going to be able to handle it.
I guess you were getting particular about the memory because if it was being stored on disk or a flash or whatever,
right.
That's why you wanted to call it space rather than memory.
Right. Space could be any kind of medium. So anyways.
Yeah, and so when we usually talk about algorithmic complexity, we end up talking a lot about Big O, which is the mathematical notation that we use to formally describe the limiting behavior of a function. But it's not just algorithmic complexity that Big O can be used for. It can be used for any sort of limiting kind of behavior that you're looking at in terms of math. So terms get a little funky. So sometimes if you Google Big O, you'll see them talking about functions and sometimes algorithms. But for our purpose tonight, we're basically going to be talking about algorithms, but we may say the word function. I just want to make it clear that like if we do end up saying function, it doesn't necessarily mean one function only. Like sometimes your functions can call other functions, and that can still be included as same part of the same algorithm. There's nothing saying that algorithm can only be one function. Mathematically, they're still talking about that high level kind of input and output from whatever calls the rest.
Yeah, and we talked about this in the past, like several episodes back. The definition of an algorithm, really it boils down to it's the recipe for what you're trying to do, right? So if it's 10 steps, 100 steps, whatever, what we're talking about is the Big O notation or the complexity for that entire set of steps that have to be accomplished.
Yep, and when I say limiting behavior, it sounds like we're talking about like actual like calculus limits and growth rates of curves and stuff. And so it's going to do a little bit of hand wave and not get too much into depth in that. But for our purposes as programmers, it basically means boiling down our algorithmic analysis to the most significant bits. So sometimes we throw pieces of our code kind of away because they don't really matter too much as the input gets larger and larger and larger.
So like some of the things that they talk about with that, right? Like if you have a few steps where you assign a variable or whatever, that stuff doesn't matter really. And so they throw it away is basically what you're getting at, right?
Yeah, which is kind of hard intuitively, at least what it was for me to grasp, because like I'll see a loop that does like 10 things inside of it. And to me, I feel intuitively like that's doing more work than something that just has one line in a loop. But that's not really true. And especially if you think about, your functions or whatever are doing stuff underneath and they're getting translated to, assembly or whatever, then it can be kind of a hard pill to think that like, we're only really looking at that loop and we're kind of not really even caring about what goes on inside there, because we know that a lot of stuff inside there can really have a big impact on performance. And that's why measuring is so important.
Keep going.
Yeah. So, I mentioned dropping those constants. So like the example there I gave where you've got a loop with 10 items in it. We don't care about the 10. We basically throw it away. We just treat it like it's constant. We say, if you've got a size 100 array or size 1000 array or size 1 billion array, eventually over time, that 10 doesn't matter because everything is scaling based on the input. And so if we chart the runtimes over time, then we should see it roughly conform to this curve. And that's what we mean when we say that we're looking at what was the phrase, the limiting behavior. Or sometimes you'll see the asymptotic analysis, but it basically means the same thing in math. When you've got that sort of curve, we're saying, you know what, it doesn't quite hit this perfectly, but it's close enough for our purposes, and we can kind of generalize and look at these things. And so coming up in this episode, we're going to look at a lot of the common types of curves and the common types of algorithms that fit those curves. And just know that, things aren't perfect. We're dealing kind of abstractly, and there's a little bit of wiggle room. But ultimately, as the input size increases, that wiggle room doesn't really matter that much. So I'll keep going.
Keep going, man. You're doing a good job.
All right. So I think pretty much covered the stuff. And here I did want to mention, I did say the testing, but what I mean by that is like, especially if you're dealing with kind of like real world business programming, sometimes there's stuff in those loops that can go out to a database or a network call or something. And so, that's where algorithmic complexity really kind of falls apart. That stuff, in a way, it's not really part of your algorithm, right? We're not including those sort of times. There's no sort of allowance in big O for that. It's just mathematical notation for what kind of stuff you're doing. And so if you do have an algorithm that fetches data as part of that algorithm, then that stuff is not going to count. It's going to get thrown away. And so what you want to do is measure ultimately.
Well, it's a measurement of the operations, not necessarily of the time. So time in regards to big O is in regards to if you're assuming how much time, if you assume that like each operation were to take a same amount of time, right? You're not counting latency for network connections and network overhead, or latency in regards to like even opening up a connection, things like that. That's not the type of things. It's just here's the operation, and then how many. If you assume a constant amount of time for each of those operations, like how bad is it?
Right. Like in one line of code, I can print a screen, or in one line of code, I could write a core dump to disk, right, which is going to be, potentially gigs. Both of those have a lot of operations going on behind the scenes that I can't see. But when I'm doing algorithmic analysis, I don't want to count that stuff. I treat it as constant because I assume that as part of your algorithm, that needs to happen. And so if there's a faster way to get the information you need, faster than a core dump, then that's something that kind of happens outside the scope of you analyzing this one particular function.
And so kind of put this in short terms, you use big O notation so that you can talk about something in a relatively easy fashion, right? Is really what it boils down to. Is you don't want to get too far into the weeds to where you can't talk about it, but once you know some of these pieces of terminology, then if you say, big O of n squared, or not big O, if you say O n squared, then people have a general idea of what's going on there, right?
Yep. So it's flawed, but in practice, it turns out pretty good, and it lets us do things that we wouldn't be able to do otherwise, and we certainly can't do perfectly.
Right.
Yeah. So as Joe said, like it's a way to describe the complexity of the algorithm in terms of time and or space, right? We can measure how well our code scales in terms of big O, right? We know if it's, we'll get into some of these, but if it's O of 1, we know it's going to be awesome. It's going to scale awesome, right? If it's O of n, it's going to be linear, right? So we can refer to it kind of like that. We can think about like how well is this piece of code going to scale? Someone had in here about it being an overloaded term now.
I think that's Joe. What you got
Yeah.
there?
Did you have an opinion about scaling though?
Yeah, if you get asked about scaling in an interview, they're probably not asking about Big O. They might be asking about like stateless web servers or NoSQL versus SQL or some of these other terms that kind of make more sense or used more often in like a cloudy or kind of architectural sense. So yeah, I just wanted to kind of mention that tonight we're specifically talking about time and space. So, almost exclusively like single processor time and something like primary memory.
So when you're talking about scaling though, you're saying, hey, if I have one value as an input and it takes 1 second, and I have 10,000 values and it takes 10,000 seconds, then you know that it scales linearly, right? That's what you're talking about with scaling.
Scaling in this regard would be the inputs.
Scaling based off the size of the inputs that you're working with. And that's if you're talking about time, right? Now, if you're talking about space, it might be that, if you have 1, then it takes up 1 byte. If you have 10,000, it could take up, 10 times that, right? It all depends. And so that's what we're talking about scaling here. So,
and speaking of 10 times, I feel like when people talk about Big O and algorithmic complexity, like 10 to 1, they're talking about the time and they're not talking about space. Space is kind of like you can do this too kind of thing.
Yeah, it's usually, but it's funny. I think when we dig into the weeds a little bit, space is probably as important, if not more in some cases, right? And one thing to point out that the whole reason this stuff even matters, because we haven't really talked about it yet, we're going to get into the weeds a little bit here in just a second, is though, when somebody says, hey, how well does that perform? Usually like, well, it's pretty good, right? But that's not an answer. That doesn't measure anything. It doesn't quantify anything. And so the whole reason we're even talking about this is because it allows you to give a more, while not perfect answer, it allows you to give you a more understood, easy to understand answer that is a little bit more accurate, right? That is quantified.
Yeah. So this is Big O in this regard is all about comparing algorithms, trying to predict their performance. So we won't know exactly how well the time is, but like you're saying, we can give an estimation of like, I think this is going to perform well because it's O of n, or I think it's going to perform bad and here's why. And we have these equations, we'll call them, that we can refer to, right? But I think Joe mentioned in the beginning though that there were more uses, right, than just in regards to computers or functions. I think is how you referred to it, Joe. This was originally created starting back. So according to I think Wikipedia was that had the creator, the authors of it, was created by Paul Bachmann, Edmund Landau, and others. And I thought, oh, that's funny. They're like, what? The others don't get any credit, right? And Paul Bachmann is no relation to Erlich Bachmann, in case if you were wondering.
Why don't they just call Paul up and ask him who else worked on it?
Right.
Yeah, right. But the thing is like he laid that groundwork back in 1894. So well before anything to do with computers, right? Like so this type of conversation about Big O doesn't necessarily have to be constrained to just software, right? Because they were just referring to it in terms of math. And so, it was over. So what they mean by that when they say it was Bachmann, Landau, and others was that, in 1909, Landau added to it. But then over the years between 1894, 1909, and then, to today, there's still been additional mathematicians that have been adding on to this functionality, right? So it's just kind of humorous though that the first two got the name credit and no one else did. But this is also referred to as the, Joe already mentioned the asymptotic notation. No, you mentioned asymptotic analysis. But Big O, this is also sometimes referred to as the Bachmann-Landau notation or asymptotic notation, which I'm having a difficult time saying that word fast. And the O today we would say stands for order of the function, but originally when Bachman wrote it, it was just order of, right? So yeah.
I actually thought for the longest time, I thought it was omega, which I don't know why. I mean, that's not the signal for omega that you usually see. So it's kind of funny that I thought that.
Because it was all mathy.
Yeah.
Yeah.
Pretty much.
Yeah, I don't know if I ever put any thought to it at all.
I don't think I did.
Yeah, usually we just talk about big O and we talk about like the upper bound or worst case scenarios, but did think it was worth mentioning that some of those Greek letters do make an appearance. So there's like theta that you'll see sometimes, or even little o or omega, and a couple other symbols that to throw in to mean various different things. But I think for tonight, we're basically just going to focus on the worst case scenario. So if we say that something is O of n, we don't mean that it looks at every single input every single time. It may look at everything but the last one. It may stop on the first. We're just saying on the worst case scenario, it's going to look at all of the inputs.
But still an approximation, as you said earlier, because it tosses out a lot of key little pieces that happen here and there.
Yeah, I mean, it could look at all of the inputs 5 times. So 5 times the number of inputs, but that's going to boil down to big O of n. We're just going to say, screw the 5, because as things get on, it's not going to matter.
Right.
So you know how great I am with numbers and examples here. So I thought, well, how can I try to make this as easy as possible, right? So I put together some examples, but I was thinking in my head, I was like, well, okay, what if we just assume a simple small array of 5 integers to try to like rationalize some of this? And then, you can expand on it from there and on your own, but to just try to get an understanding like what some of this is, right? So we're going to go through some of these orders and we'll start with O of 1 first, right? So O of 1, this is constant. The operations aren't affected by the input size. It doesn't matter, that 5 integer, that array of 5 integers, it could be 5 million, it could be 500, doesn't matter. If the O of 1 operation is still going to take the same amount of time regardless. So for example, using that 5-digit array, or that 5 integer array, accessing an element in that array would be an O of 1 operation.
Because it knows just where to go. It doesn't have to do any kind of scan or anything like that.
Yeah. So you remember back, it wasn't last episode, I guess it was maybe 2 episodes ago now, where I brought up about recall the conversation that we had about like, why do arrays start at 0?
Right.
For a lot of languages, right? And hint, it was because it was a memory offset, right? And so that's how the array operation is able to be an O of 1 operation, right? Now, again, arrays, not lists. We're not talking about any kind of linked lists or anything like that, or specific list implementations. Like, let's just keep it simple and talk about arrays,
right?
Yeah, and just wanted to give an example of the kind of size here, or the kind of time performance we're looking at. So if we take that array of 5 integers, we pass it to a function. Let's just say that function just returns false all the time, no matter what. So it's going to take 1 second. So it doesn't matter if that array is 5 or if that array is 50,000. No matter what, it's always returning the same thing. So it should always take about 1 second.
Yeah. So this type of operation is considered constant time. Because like Joe said, it doesn't matter what the size of that array is. So one of our, I would have to say collectively, our favorite resources, we've definitely talked about it a lot. Definitely one of my favorite resources is the bigocheatsheet.com. So if we were to look at there, they have all of them graphed out, right? O of 1 operations are very green. These are very quick, fast operations. Right. So we like these. You
don't really get any faster. Right.
Well, do you? I actually looked up to see if there was O of 0. And there's quite a bit of debate like on Stack Overflow. I don't know what the mathematicians would say, but it seems like the Stack Overflow arguments all lead to you can have it if it just doesn't ever do anything.
Yeah, I was going to say, what's the use of it? It sounds like, you could totally do it, but it'd be completely useless. So,
yeah, I don't understand what it means to have 0, 0. It's like, are you saying that it never returns anything because it's like a syntax error? It doesn't make sense to me. So if you can explain that, I would love to see it in the comments.
all right.
Yeah, I don't get that. I'm trying to think of I was trying to think of something clever to say it's the else statement that never gets executed, or it's like if true equal false, and then you have a block of code, and that's O of 0 because it's never going to happen.
But it still counts as one operation because you're doing the if nothing else.
Well, I was thinking about in the block though.
But you got to remember,
in the
you're
block,
tossing it out on big O anyways. That if wouldn't matter typically. So yeah, it doesn't make any sense really.
Oh yeah, you're right. The if wouldn't count.
Yeah, it wouldn't count. They dropped that off. Yeah.
But when they say drop it, it doesn't necessarily mean like turn it to 0. Like otherwise you'd be multiplying 0 by whatever. So it's like turning it to a 1.
No, but no, Alan's right though, because the size that any kind of if equals false type of operation like that wouldn't count in terms of calculating big O because the input size doesn't matter.
Yeah, we sort of glossed over it earlier. When you said when you set constants and stuff, like typically if in your function you have if this equals 1, then do this, or if this equals 2, they basically say those operations don't count. They're insignificant for the grander scale of what n number of inputs are. So all those if statements and all those operations get thrown out the window for big O notation. So yeah, there again, going back to O of 0 means nothing as far as I can tell. So
I mean, because we have it summarized here in a different way. Because using my joking example of if true equals false, that would be considered a constant, so it wouldn't matter in terms of our growth curve.
Right.
So that's why we wouldn't count it.
So I think going back to what we were originally saying, I think O of 1 is the constant is the absolute fastest that you can aim for, right?
Until Stack Overflow.
Yeah. In a useful operation, I guess. Yeah. All right.
Yeah.
So the next one
Joe sounded a little unconfident with that. He was like, "Oh, we're gonna get some backlash."
Yeah, I'm gonna get spanked.
Here comes the O of 0 crowd.
Joe will be there, or Jerzak will be there to field any kind of questions in episode discussion.
Yeah, if I talk about math, I end up saying something wrong.
Yeah, I think we did in the last episode, which was called out to us. So
check it out.
Yeah, check it out.
Check it out.
All right, so the next one we have up is O of n, also called order of n, which I think O of 1 is also called order of 1. So
I've never heard that though. Never ever. I've always just heard O of 1 of O of n.
Yeah, you'll probably hear, at least in our realm, O of n. So the order n operations take more time to run for larger inputs, but the growth rate is what they call linear. As the number of inputs go up, so does your time. So it's basically the example I gave earlier. If you have one input, it's 1 second. 10,000 inputs is 10,000 seconds, right? So linear is as it goes up, you have a nice graph to where the line's just going up at a good 45 degree, right? Assuming that the scales are all right.
Yeah, I did a little bit of math for each of the sections that we're going to talk about, each of the orders we're going to talk about today. So just to kind of keep consistent, like for the constant time, for input of 5 in our array, it's going to be 1 second. 5,000, it's also going to be 1 second. For order n, now this is really easy. It's for input size of 5, our array, it's going to take 1 second. And then for an input size of 5,000, it's going to take 1,000 seconds. It gets a little weird because of 5. Sorry about that. But yeah, you can see it.
For 1 second per input, it'd have been a whole lot easier, man. I'm just saying.
I didn't realize that there was an example above that specified 5. So,
oops.
Yeah. All right. So that's gonna stink. I'll figure something out for that for next section.
All right. Well, but yes. So it's pretty easy in that particular sense. So
yeah. So this is an operation where you need access to each element of this. So let's go back to the array example. Now, keep in mind, I'm just using an array as a way to easily discuss these from an example point of view. But these O of 1, O of n operations, it doesn't have to require an array. It's just easy to reason about it if we use that as an example. So going back to the array of 5 integers example that Joe doesn't like, that threw him off. If what we're saying here with O of n is that you have to access each one of those. So if you wanted to sum up the array, then you need to access each element of the array in order to add it to your running total, for example, right? Or if you wanted to, if you assume that you didn't have let's let's assume that the array was full of random numbers that aren't sorted, right? And you just wanted to find the smallest one. Well, in order to find the smallest number in that array, you'd have to visit each number to see, is it smaller than the one you're currently, claiming to be the smallest, right?
Yep. So what he's basically saying here in a nutshell is if you're looping over a collection and you're hitting every item in the collection, you're automatically at O of N. Best case scenario, you're at O of N.
That's one way to put it, yeah.
What I think is really interesting here is because
that's a really good way. I was joking.
Well, because we dropped those constants, if you take your input size and say half it or divide it by 3, which is going to drastically reduce the amount of time it actually takes to run, it still doesn't count. It's still considered O of N. So if you say, let's say you create a function called max number good enough, that only looks at the first half of the array. It takes the biggest number it finds there and says, you know what, this is probably fine, and returns it. That's still on order of n, even though it only ever looks at half the input. And that's because you're dividing by a constant number.
Is that true, though?
Totally.
I don't think I can argue this one. But that's
I miss it because I was reading something else.
He was basically saying if you were to say that I'm only going to go through the first half of this particular collection, then it doesn't matter because you're getting rid of the constant. You're basically throwing it out. You're still saying it's O of N. But the only reason I'm struggling with that is we're going to get into the O of log n here in a second, which is the whole divide and conquer thing, which is what it sounds like you're saying, though, right? Like that's so. So
the difference there is that divide and conquer means you divide and you divide and you divide and you divide and divide and you keep dividing until you get to your result. And so all I'm saying is you divide by once, a constant. It's not a factor of my input. I'm not saying divide by, the logarithm of the
use case of this.
There's not. He was just making that up.
No, I mean, like the one I think the example I said where like you only look at half of an input. I mean, that's totally contrived, but you can think of like some sort of heuristic solution to an algorithm or to a problem that's similar. Where you say like, I give up after so long because this is going to be good enough. Because say you're like in a real time context or something where you've got to make a decision in 1 second, like you're a AI in a game or something, and you say, you know what, here's your time bound, and so if you don't get through the whole input, just give up. Who cares?
I could see where you do something like that with photos when you got pixels and color ranges. Like, you might skip every second pixel because things that are that close to each other might not matter that much. Like, I could see where you do something like that. So, but okay. So I get what you're saying because you're not constantly subdividing and you're only doing it the one time. You're saying, hey, divide this by 2 and then go. Then that constant gets thrown out. And so you're still at O of N. Yep.
That's because when you chart it on the the graph of time there, it's still going to form a straight line. So it's still going to be linear. It's just going to be half of what a normal slope of 1 and 1 would look like.
And that makes perfect sense because really what you'd be seeing is an equation that said O of n divided by 2. That divided by 2 gets tossed out the window. So you're totally right. So that's O of n.
So I think what we've already said then is that this is a linear operation. And that, because as the size of n grows, so will the number of operations. Now, I'm going to reference Big O cheat sheet multiple times in here because I love it. And this is in our yellow range.
So does this mean you should not use it?
It's fair. You can use it, but you should definitely be aware, right? If you're doing it, if you have to go over everything in the array or your collection, as you so eloquently said, then you just need to be aware of like what your expected sizes of that collection might be, right? So that you can be aware of it.
Yep.
All right. So let's get into a fun one then. So O of 1 and O of n, those were kind of easy, right? From here on, they're going to get weird and fun, right? But in a good, that's the kind of stuff that we like. So O of n squared, right? Wait, who put this?
Oh, that was me. I augmented the notes a little bit. Sorry, dear listeners.
Okay, yeah. So Yeah, I'm totally thrown off now.
All right, Joe, you take this one.
Yeah.
And then
Yes.
on track in a moment.
So
Sorry.
for constant time, order of one, then you don't have to look at all of your input. That's how the way I kind of think of it.
Right.
Like the input size doesn't matter because you're not really looking at your input. You're either returning the first element of your array, or you're returning a hard-coded value, or you're doing something else entirely. And in order n, we said you look at most at all of your inputs once, at most. So n squared is the worst case. You're looking at each input for each input at worst.
Right.
Right. So, okay, I see where you're going with that now. So let's go back to my 5-element array example, right? And suppose that you wanted to return back a new collection that paired up every number with every other number in the array, including itself, right? So, your numbers in the array might just be 1, 2, 3, 4, 5, but you want to return back pairs like 1, 1, 1, 2, 1, 3, etc., up to like 5, 1, 5, 2, 5, 3, etc., right? That's what Joe's describing, is that you have to have a loop that goes, an outer loop that goes over your array, and then an inner loop that goes over it a second time in order to pair those up, right? And that because you're doing that second loop, you're going over every element again. That's where you get into n squared. So that 5-element array, you're going to go over it 25 times to produce that pair.
Yep. So 2 things. One, did anybody else here 1, 2, 3, 4, 5 think that's a combination of my luggage? So that's one. But if you've ever seen the code where you'll see something like for I equal 0, I less than, array.length, and then I++, and then inside that you'll have for J equal 0, J less than array.length, J++. That's exactly what he's talking about. You've got 2 nested loops, or you've got a nested loop that are both going over the same array thing the same number of times, and then that's how you get into this n squared problem.
Right. So if another way to say that is the outer loop is doing it n times, and the inner loop is doing it n times.
Yep.
Therefore, it's n times n, which is n squared.
Yep.
And if you remember when we talked about bubble sort, we said that it was a worst case scenario of n squared because every number looks at every other number. But what's kind of funny about that is when you say that, you kind of gloss over the fact that you never compare a number to itself. There's nothing to swap. There's nothing to do. So in an actual bubble sort example, if you actually like console log to every operation, you're actually not going to see 25. I think you'd probably see 24. I could be a little wrong on that, but might be less. But the deal is, you don't compare the first number with the first number. So like your outer loop starts at 0 and your inner loop starts at 1 because there's no point comparing. So it's just kind of one of those funny cases where the actual, quote unquote, actual big O would be n times parentheses n minus 1. Well, because you drop those constants again, you just end up with n multiplied by n. So n squared.
Yep. So, and this operation is highly efficient? Yes? No.
No, these are not considered efficient.
In fact, almost every time I've had like an interview whiteboard problem or some sort of interviewee tech problem, they give you a solution that kind of has an obvious solution where you're like, oh, I could do it this way, and it's n squared. And it pretty much any time in an interview you see an n squared problem, you can get that thing down to n log n, if not lower.
Yeah, and that's the key, is understanding that you're looking at nested loops and that, oh, this is going to be n squared. And that's the first, just like what you said, that's the first thing the interviewer is going to say, hey, what's the complexity of this? And if you can't look at it and say, oh, that's n squared, then that's going to be like rule number 1. They're going to be like, oh man, this guy doesn't even really know what he's looking at. And just knowing the notation, knowing the naming for this is going to be a big one. And then you look at it and you say, oh, that's O(n) squared. And then they're going to say, well, can you make it better? And then you're going to have to go, oh yeah, I think I can.
But I do want to like make one clarification there though. It's nested loops over the same
set.
collection.
Yeah.
Right. Just if you see a nested loop, that's not necessarily in and of itself. It could be
2 different collections, right?
Yeah. That doesn't necessarily in and of itself equal O of n squared. It could still be very bad.
Yes.
But it's when we have the same list that we're iterating of, that's when it's guaranteed. You're looking at O of n squared.
Definitely.
Yeah, and actually, we keep talking about n as if like that's always the kind of the inputs to a function. But if you remember the graph algorithms, some of the complexity there in time would be like the number of nodes times the number of vertices, or something like that. And so the inputs, you can slice things up differently if you're a math whiz, and I am not. But if you had, say, an example of a function that took 2 arrays and multiply the 2 by each other, then your algorithm complexity might be like, well, it's the size of array 1 multiplied by the size of array 2. And sometimes in some algorithms, like you'll actually see them specify it like that way. So they'll say like big O of m times n is a common one. They'll use the letter m. And sometimes you'll see them say like, yeah, they're both inputs. Screw it. Let's just call it n squared.
Right.
Because math is ambiguous.
It can be.
There's probably some solid rules on when they differentiate like that.
So where does this thing land on the big O cheat sheet?
Now we're getting into the reds. This is let me say, of your bad scenarios, this is the best of the bads. How's that? Does that make sense?
Yep, that does.
Like if you had to go down a terrible path, this would be your best of the worst choices that you had.
Yeah, and I kind of put it in perspective. If you remember, I'm just going to simplify and say for input size 1. So our constant time, input size 1 was 1 second. 1,000 was 1 second. For linear, our input size of 1,000 was 1,000 seconds. Now, our order n squared algorithms, it's going to be 1,000 times 1,000, so 1 million seconds. That's a lot of seconds.
Yeah, that really is. For 1,000 inputs, right?
1,000
so
inputs.
Now went from 1,000 seconds to 1 million seconds.
Yep. Spline the kind there.
Yeah, that's a pretty big deal.
I totally forgot. We're talking about these 1 seconds and the input size, but we actually covered this last episode.
Yep.
I think we did, yeah.
With the
It wasn't last episode, but it was a couple of days.
It was Jeff Atwood's Everything is Fast for Small N. You and I discussed this.
Did we?
And we were saying that for O of, if n was 1, then it was less than, for n, where are we on? N squared?
Yeah.
So if n is 1, it's less than 1 second. But, for n of like 16 million, it was 8,923 years.
Right. It's ridiculous. So these n squareds get big, right? And like Mike said, this is not even the worst. This is just where you're dipping your toe into the red. It goes really bad after this.
Well, it's more than dipping your toe. It's very much in the red.
Yeah, you're in the red.
But of your other alternatives, this is like the best.
That's it. I totally like. This is the where I will stop writing. I won't go worse than this in like code I'm doing. So I'll absolutely write n squared code sometimes because it's faster for me to write and easier to debug. And I'm sure there's better algorithms out there. But if I'm dealing with, say, a max of 50 items in my array, and I know that I'm never going to go more than whatever, then I don't feel too bad doing nested for loops for something. I know it could sort it ahead of time and get that to n log n, like with merge sort, and then loop through it again. So it's n log n plus n. So we drop that second n because it's the same as saying 2n log n. So just drop the constant. Sorry for that divergence, but yeah, so it's n log n. So it's absolutely faster, but for input size of 50, you're not going to see that benefit and the code is going to be miserable.
And that's true.
But I mean, to your point though, we've all done, this is why I was saying of the worst case scenarios, O of n squared, it's bad, but if you had to go down a bad path, this is your best choice because, we've all written code where we've gone over that collection multiple times because as we're in the process of developing it, right, you're in the creative kind of mindset and you're just like, let me get the thought out, right, as to like how this might work. And then you can come back and start refactoring it and tweaking it as you go along, right? But your first iteration, maybe it's not ideal. And your initial iteration, you write it O of n squared. But again, like Joe's saying, you're probably not right. You're working with large inputs in the beginning, as you're developing it, right?
And this is where knowing the use case matters a lot, right? What you just said about writing code that's going to be nasty or gnarly to look at, right? Like there's always a trade-off, right? There's the readability of the code and then there's the performance of the code. If you know that thing's never going to grow past 50, and in real world scenarios, these 50 iterations twice isn't at 1 second per, right? Like we're saying 1 second just so that it's easy to do the numbers. But, when you're talking milliseconds, okay, it's probably not going to kill you if you just have an array or a collection of 50. But that's when you have to know, like, oh, well, wait a second, this thing's going to start growing because we're going to get, now we're dealing with customer orders and we plan to one day have 1,000, per hour or something. Who knows? So you just kind of have to know about these things and plan for them as best as you can.
Again, going back to Jeff Atwood's graph here or table here, if we assumed that the input instead of 50 was 256, then n squared is 65 seconds,
right,
according to each one being a consistent unit of time,
right,
equal to 1 millisecond.
Yeah. So I mean, to each their own, but just be aware of your use case. And I like what we got here. What about O of n to the third, O of n cubed? Is that a thing?
Yeah, absolutely. So when we're talking about O of n squared, we don't necessarily mean just a nested for loop. It could also be n to the fourth or n to the fifth or anything in polynomial time. So just wanted to kind of call that out. Like most of the time, though, most things that we look at, it's just going to be n squared. So that's kind of like the most common thing. And so like with all the stuff we're talking about today, like all the examples of the curves, like there's all sorts of stuff in between that we're kind of skipping over just to kind of keep things reasonable to talk about. But these are generally the rough classifications of algorithms. So there's like big groups and so things like hash table lookups and array lookups, like those tend to be constant. Sorting n log n is kind of like the de facto kind of standard there. N squared is kind of getting into the stuff where it's like there's almost, at least in every interview I've ever been to, there's almost always a way to get that thing to way faster. So like n squared is kind of like the there's a better way to do it zone.
You know what's funny about this? Where I see this stuff happen a lot that's typically just accidental or lack of knowledge or just not knowing what people are doing is when you have something like an array or some sort of underlying storage mechanism and somebody does a count on it, or something to where there's not some sort of indexer that gives you the thing. I don't think counts one, but like if you have an IEnumerable, in C# a lot of times it'll tell you, hey, be careful because you're probably going to have to enumerate this entire thing to get the count. And
right.
You'll see people do it 2 or 3 times in a method. And you're like, oh my God, like, dude, get the count of that thing, store it in a variable, and then use that later, right? So you kind of have to be aware of the constructs or the data structures you're even using because you might be doing this and not even realize it, right? Like you might even not have, like you said, nested loops. You might just be calling the same thing over and over, not knowing what the underlying operation is going to be.
And actually, one of the most common things that I do correct when I see them is if I see things that are using arrays and they keep looking up something by a value in the array. And so they'll say they'll iterate through the array to look for an object whose key equals 1, 2, 3. And so you'll see, a bunch of lookups that happen in a loop and they won't cache it. And so it'll be like 100 times and it's looking this up. And as you know, that's a linear time. So as that input size grows, then you're doing a lot of extra work. But if you convert that thing to a hash table, which has constant lookup, then that's a huge savings of time. And it's often something that's really easy to do. You just kind of pay the hit to enumerate from that array to a hash table once, and then lookups are cheap ever after.
No,
wait a minute, though. I missed something there with your example because an array lookup would be constant
by value,
by index.
Oh,
by value.
I'm sorry, that's the part I missed.
Yeah. So the interesting thing though is, and that's where you start getting into the other side of the equation, which is you were initially talking about time. Now you've doubled your space, right? Typically, we'll say if everything had a unique value, then you've just doubled your space because you got the same amount of data in your array, and now you have the same amount of data in a hash table. But assuming they're all unique.
If you're dealing with reference types, so like objects on a heap, like you don't duplicate the whole object. You have a separate pointer to the object on the heap, but you're not making a duplicate copy of every customer record.
Oh, you're talking about just pointing back to the array. Okay.
Well, I mean, not necessarily in the array. Like the array is going to be an array of, if it's a complex object, like in C#, it's going to be an array of pointers to the heap,
right?
Those objects. And in the hash table, it's going to be pointing. So if you modify the object at array index 5 and change the customer's name, it's also going to affect that hash table because they're both pointing to the same object.
Okay, so that's where, God, it's been a long time since we talked about the stack versus heap, but this is where you kind of have to know your constructs of your language too, right? So if you had complex objects like that, it would be pointing to the heap. So anything referencing that would all be pointing to the same objects, which is what he's saying. So you don't double your space. However, if you had an array of primitives like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, and you put that into a hash, then you are doubling your space because that's all going to be on the stack, which is, operating at the current function. So, yeah, I mean, a lot of this stuff goes really deep, but it's, again, there's a trade-off, right? Do you keep scanning the index of the arrays to find the stuff, or do you just put it into separate storage and then know that you can get to those values immediately on constant lookup time, right? So,
yep. So that's kind of like a neat little shortcut. I know anytime I see like some sort of linked list or array index lookup by value, where it like looks at each one and looks at it, I know that's easy hash table replacement. So if that's something that's going slow, like in the UI, it's kind of hanging the thread, and that's something I'm going to look for. It's just an easy win.
Yep. And when you say this is all very language dependent, right? Like,
yeah. And hash tables are their whole other thing. We're not going to get into that because a lot of it depends on how efficient the hashing algorithm is and collisions and yada yada. So,
yeah, but then you've also got dictionaries and map objects.
But data structures would be a good conversation to have.
It would. I mean, it actually takes this to the next level to where you can probably do more with what we're talking about right now if you actually understand the underlying data structures.
And, I was looking, you mentioned about heap versus stack. Did we ever I don't think we ever did like a topic specifically on it. I think it was just like a byproduct of like
value and reference.
Boxing and unboxing
conversation, right? So the boxing and unboxing conversation was episode 2.
God, that's been a few.
So
it's been a few days ago.
It's been a couple episodes since we've talked about it.
I don't know. Maybe we do something like that in the future. I mean, it's definitely something that if you're not aware of can really bite you over time. So, anyways.
All right. So, hey, I'm going to take a quick break and ask you to leave us a review if you haven't already, because we really appreciate it. It helps us grow the show, helps us find new people, helps us keep doing what we're doing. So if you like what you hear, then drop a 5-star review in there, and that would help us out. And if you don't like it, drop a 5-star review and send us an email, and we can talk about it.
All right. So now we head into my favorite portion of the show, Survey Says. All right. So last episode, I asked, does having multiple monitors improve your productivity? And your choices were absolutely. And on the bright side, pun, I get to work on my tan from all the extra UV light. Or no, but it can be a nice luxury. And lastly, it depends on the code base. The smellier the code, the more monitors I need. That and air fresheners. All right. So, Joe, you weren't here last week or last episode, so I will let you go first.
Okay.
Which one do you think was most popular?
Absolutely. It does improve your productivity with 43%.
43%, absolutely.
Dang, son.
Even though I use one.
All right. I'm going to go with absolutely, and I'll go 44.
44. Wow. He's going to oversell it by one.
Price
43
right,
44.
man.
Price is right rules.
That's right.
All right. Well, I'm sorry, Joe. Alan wins.
Yeah. How far was it? Is it 60s? 65?
83% was absolutely.
Did anything get 0?
I mean, surprisingly, it depends was like really close. It wasn't very much. So, I mean, it wasn't 0, but 0%, but it definitely didn't have a lot of love, which I was surprised about. Like, which one did you guys think would, like, how do you honestly feel? Like, what's your answer?
Absolutely.
You absolutely think it makes you more productive.
Yeah, man, definitely.
But Joe, you just said you only use one monitor. So why?
Space. That space is also important to me. So I'm taking a productivity hit for a little bit of sanity.
Gotcha.
I have an option for you. Just buy like a 50-inch 4K. Then you're good.
Yeah, I
Yeah.
don't know about a 50 inch. I am looking for a new monitor, and I was thinking about getting a like a 40 something 4K monitor, but I really kind of want a curved because so I had to get rid of the LG sadly, and so I'm looking for something to replace it, and that's why I'm down to the one monitor. But I'm kind of like, I mean, if you're working on a laptop, you only have if you were using just the laptop, right? If you're out and about, you only have the one monitor. So are you saying that you can't be productive on just your laptop?
I mean, you know what? You're not as you all tab a ton when you're on a laptop, right? I will say though, and I mean, Macs have had this forever with the virtual desktops. Those help a lot, and on Windows too.
Windows has it too, yeah.
Yeah, and so Windows introduced it. I don't remember, maybe last year. I can't remember, but using virtual desktops really is nice. And on Windows, like on Mac, I just would 4-finger swipe to the various different screens. On Windows, you can Windows tab to get to them,
Or Windows Arrow.
or Windows Arrow.
And just like on Mac, you can control
No,
Arrow.
Windows Arrow doesn't do that. Windows Arrow moves my windows around on the screen.
You can. I want to say it's like window control window arrow.
That's what I do on mine.
And you can change between desktops, or you can window tab, and then it'll bring up all your desktops. But and depending on what drivers you have, like if you're on a laptop, for example, with a touchpad, the drivers there might also support like a 3 or 4 finger swipe to go from one desktop to the other. But also on the Mac, you can just press Control in the arrow and you can flip between desktops.
Hey, so here's a little tip for you. God, this is the wrong time to show, but on the Windows tab thing, one thing and one of the reasons why I didn't adopt the virtual desktop on Windows sooner was because my Outlook would be on one screen and my Skype would be on one screen. And so somebody would instant message me and I wouldn't get it, right? And they're like, man, does this dude ever work? Right? I'd come back over my screen like, oh man, he wrote me 2 hours ago. You can, if you Windows tab to where it shows you a list of all your windows at the top, you can right click on an application and say, show on all screens. And then that way, your Skype, your Outlook, and all those things will be available on every screen you go to, so that if you do get a notification, you'll know about it. So
I actually find that Skype and Outlook aren't so bad though in particular scenario you're describing, because they're pretty good about, at least without having to do that show on all desktops that you're describing.
They wouldn't show up on my other ones.
But I actually kind of like it. Like when I use the multiple desktops within Windows, it's because I want, like, here's my communication quote communication window,
Slack,
desktop,
Skype.
Here's my coding desktop, right? Just to like keep the worlds of sanity, keep those things separate so I can stay sane. Because otherwise, it can really be frustrating if you're trying to like stay in some mindset while you're working through a problem, and then you see a Slack or Skype or email come in, and you're like, all you got to do is see like just the first line of it, and you're like, oh, I didn't know what that is. I want to read the rest of it, or I want to respond to it. And you're like, oh man, now I'm out of it.
I might have been late for my scrum today because I was kind of I was just sitting there working, and I get pinged. Hey, you coming? I was like, oh yeah, my bad.
But no judging.
Yeah, no judging. All right.
So let's do today's survey. Is how's your math? So your choices are: there's an app for that, or was great in primary school. Now, who calls it primary school?
Yeah, man.
Hey, really? we're international friendly here.
Oh, is that what it is? I'm sorry.
Good call. Way to be PC, man.
Man, I'm going to hear about that. Dang. Your third choice: I can tip 20% comfortably, or I can still find the area under a curve. And lastly, I can still log of E with the best of them.
That's ln of E. That's the natural log.
Oh, sorry, I misread that. So see, I already failed. I can still natural log of E with the best of them.
I am curious what the results of this one are going to be, and I'm going to guess right now that neither me nor Joe will get this answer right.
Yeah, I should have said I can tip 20% uncomfortably. I added a digit somehow the other day, and I was like, oh wait, that's like $1,000 tip. What's going on here?
That's because you're a baller.
Oh no, that was a mistake.
All right, so let's go ahead and jump back in here. And the very next one is where things start getting a little bit more interesting, like Mike said. And we have O log of n. And I think we mutilated this a little bit before, although I think we got to the right answer. So when we're talking about big O notation with log of n, we're talking a base 2. And when we're talking about software terms of this, right?
Yeah, and what we mean when we say log n's, we're kind of skipping around a little bit in terms of growth here. But what we mean is that we're just talking about log of n, logarithm of n. So we're only looking at a fraction of our input. And this is the one where it's very different from looking at just half your input, because what we need to do is kind of keep dividing. So an example here I like is looking up something in a dictionary, where you kind of flop that big book open, if you remember what those are, and like your words in the S's, and you see you're in the P's, and you need to guess again and kind of flop a bunch of pages to the right, and like ultimately you only end up doing like say eight page flops to look up something in a 1,000-page book, which is really efficient, really nice. And that's an example of a log n. That's different from divide, because if we were to divide that dictionary in half, you would still look at like 500 pages of that 1,000 looking for your item.
So this is like an example of like a binary search, right? It is kind of what you're talking about, like this divide and conquer approach to things, which we talked about, I think, 3 episodes ago.
Yeah, we talked about that one recently. Another example, another real world example that we talked about it at the same time was get bisect.
Right. So again, like Joe said, just splitting it up and keep making the thing smaller until you get to the answer you need without having to go through every single item in your collection.
Yeah.
In fact, if I remember correctly, Joe, when we did discuss this, the binary search type of divide and conquer type of operation, used the phone book analogy, right? Where it was like, you're going to skip to what you think is going to be the right, and then you'll divide that. You'll keep dividing until you get to about where you need to be.
Yep. And so to kind of put this in perspective, this ends up being slower than constant time, and it's going to be less than linear. So it's sublinear. So it ends up being between O of 1 and less than O of n. And kind of an example here to kind of put that in terms of seconds is if, our old 1 input 1 second example, for a 1,000 size input, it's going to take 10 seconds. So compared to linear, which for 1,000 took 1,000 seconds, that's a huge difference. So log n isn't just a little bit better than linear. It's way better. It's much closer to the constant line than it is to, oh gosh, I don't know if that's true. It feels like it's much closer to the constant line than it is.
Okay, so let me go back to the Jeff Atwood example then, where each unit of time was 1 millisecond of CPU time. Then for every size of n that he has listed here, from 1 to 16.7 million, O log n is less than 1 second for all of those.
So yeah, it is. What you said is actually very true. It is very close to constant time, even as numbers get outrageous. And I think, Mike, don't you have the big O cheat sheet thing on this one as well?
Oh yeah, this is green. This is very green. This is where you want to be.
And it's literally like, so going back to what you just said, Joe, like if you look at the big O cheat sheet, like the lines are so close to each other, they basically just put a comma between the O log of n and O of 1. So
yeah, I just looked it up, and so I feel much better. It is indeed much, 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 much closer to constant than it is to just n.
Yeah. And since we're talking about logarithms here, I wanted to at least like maybe remember like how what this is, right? So if we were to say that we had x to the third power equals 27, and we wanted to try to solve for x, then we could say, okay, fine. Well, it's x to the third, so it's being cubed, equals 27. So we could take the cube root of 27 to solve for x, right? But if we were to flip those around and instead we had an equation that was like 2 to the x equals 16, right? And now we got to solve for x. Well, that's the type of problem that we're trying to solve That's what logarithms are solving for us. That's what this is doing for us. So, this is when we say that the 2 to the x equals 16 is, well, how many times do we have to multiply 2 to get to 16, right? Is that making sense? Is that helping, you think?
I mean, yeah, that's your logarithm would be log 16, right? Is what you call it, base 2 here.
Yeah, base 2.
Yep.
Yeah, it scales super well. I mean, it's almost flat as things kind of stretch on. So, yeah, logarithm is really great. And you'll see a lot of really great solutions to algorithms. You'll start out with the brute force solution, which will be like n squared or polynomial. And someone will figure out, hey, if we can convert this to a log n problem if we also do this. And so they'll loop over the input, or they'll sort it first and do something that lets them kind of sneak this log in there somewhere, preferably inside an inner loop. And so that's kind of the secret. And so if you're kind of used to dealing with these algorithmic complexities and looking at big O, then you kind of know, like, whenever you see an O of n squared on something like an exam or an interview, like, be looking for a way to reduce that inner loop to a log n operation, either by sorting or doing something like a binary search, or doing something to reduce the inputs that you look at and reduce duplicate work. And so, yeah, it's really important to look at those log n's because they scale so well. It makes things so much better.
So when we use that array of 5 integers, right, as just kind of like a baseline to discuss some of this, right? And in that example, with that array size of 5, if we did an operation that was O of log n, we're only going to have 3 operations on that, right? So you could see how, like, the O of n would be 5 operations, and now O of log n is 3. So we've already cut it down. And this is where the scaling comes in, where Joe was saying, like, how much better it gets, because if n was instead 100, then we'd only have 7 operations.
Yeah, only 2 more steps for 95 more for 20 times the input size. 2 more steps. That's amazing.
Or 4 more steps.
Yeah, 4 more steps.
3, now 7. Yeah.
See, well, you know where math is hard.
That's why there's a for that.
Yeah.
Well, it's easy enough to visualize, right? Because let's just put out numbers a little bit real quick. So 2 to the 5th is 32, right? 2 to the 8th is 256. So adding 3 more, you got to 256. Now let's just do 2 to the 12th here, just for the heck of it. And it gets big really fast. So where did
4096?
12th. Yeah, so 4096. So 12 operations would get you 4096 inputs, right? And that's kind of what we're saying is, even as the number of n grows, like 4096 n, that's only 12 operations there. If you did 2 to the 20th, right? 20 operations would get you in the ballpark of 1,048,576 inputs. So 20 operations. So that thing, 20 operations for over 1 million inputs isn't much worse than when we were down at 12 operations for, what was that number? 256, I think.
Oh, for the
2 to the 12th. I can't remember now.
Oh, 2 to the 12th was 4096.
4096. So yeah, man, you had 8 more operations and you were able to do, 2,000 times the work. Like it's kind of crazy. So yeah.
Yeah, you're like, hey, here's a book with 4,000 names in it. I need you to find me something. And I'm able to say, yeah, I only need to look at 12 of them.
It's going to take me 12 seconds, right? Yeah.
At worst.
At worst, right. Right.
Well, when you put it like that, Joe, it kind of reminds you of those type of questions where it's like, I'm trying to think of a specific example, but like the, what's not the state fairs, but the carnival type questions where it's like, hey, I can answer this, and like, I can answer something about you in X number of questions, right? Where
I'm terrible at this.
It's like the trick things. I always think of name that tune. I can name that tune in 3 notes.
And when they do it in 1 note, you're like, what? Nobody can do that. How's that possible?
Yeah,
that's really cool.
And everyone listening is like, what's the name of that tune?
All right. So I think
You're not gonna touch that.
no, we're not. So the next part, I think we need to skip this piece right here because it leads right into the next one, right? Like kind of takes over it. So who wants to pick up on the next big O notation thing?
I could do that. So we kind of talked a little bit about n squared and how a lot of times you can kind of reduce those problems. And so you take one of those loops that's looping over your full input and you figure out how to half it and half it and half it and half it, or take some sort of subdivision of it and get that convert that inner loop into a log n operation. And then if you're still keeping the outer loop, and you got to n log n. And this comes up a lot, like all the sorting algorithms, like a lot of famous algorithms are all basically kind of riffs on that notion where they take some sort of brute force solution, which runs in polynomial time, and they figure out how to reduce part of it, and they shift things around, and then you end up with the n log n operation. And what that means is, a kind of example you can think of like crudely is that you take an array of 5 numbers, and you loop through each of those 5 numbers, and where you would in the n squared algorithm will have looped through those 5 numbers again for a total of 25 operations. Now we're saying we only need to look at half and a half and a half. And so what is that, like 1 or 2 operations?
On the inner loop, right? So you're talking about, you're still going through the outer loop of your 5 elements, but then your inner loop, you're going to use something like some sort of search, right? Something goes in. And so now you're splitting that thing. So your outer loop is still O of n, but your inner loop is now O log n, right? And that you can't throw away. When you've got 2 of these things, now you have to multiply them together. And so your O of n times your O log of n is now O n log n, which I think is what me and Michael were talking about last time, where I was like, wait, I think that'd be slower. And then I got called out many, many times, say, no, it totally can't. So just, that's where, again, what you were saying earlier, Joe, about things falling in between, right? This one falls in between O of n and
n squared polynomial.
Yeah, O n squared. So
yeah, and unfortunately, it's much closer to the n squared in this case. So it's not a great curve. It's not nearly as close to linear as other ones, but it can have a really big impact. And for example, for that 1,000 input size, the 1 second thing, the n squared was 1 million seconds. This is 10,000 seconds.
It's big.
Yeah, so it's big. 10,000 seconds is a long time. It's much worse than our 1,000 seconds. It's 10 times worse in the linear case, but it's still nowhere near a million. So it's much better than n squared, but it's not great.
Yeah, I mean, this is, going back to our big O cheat sheet, this is in the orange category. So it, and in fact, the way they have it drawn there, it's closer. It's not exact, but it's closer to the 45-degree angle. I think I heard someone mention earlier.
Yeah, I said that, yeah.
It's not a 45, and it's actually a curve, not a straight line, but it's closer to it, right? But definitely in that orange area where this is probably bad. You should be concerned, unless you absolutely need to do this.
And if you're in an interview, they give you the problem to solve. You figure out how to do it n squared, and they say, can you do it better? You say, yes, of course. Here's how I get to n log n. They might ask you, can you get it better again? Now, this is the point where if you look at the problem, you might be able to figure out some sort of really clever solution and say, you can get it down to n time, but they usually won't have you coded. So, if you're in an interview, it seems to always or often follow this kind of pattern when they give you obvious brute force, you get it down to n log n, which is much better. And sometimes there's a clever solution that you might be able to identify and relate that is going to go faster than that, but usually that's going to be really tricky and really hard. But it does seem like a lot of the n squared problems that you run into, either out in the real world or kind of in interviews or like code wars, a lot of them can be reduced to n log n. That's a definite strong pattern there.
And just as a heads up, what you said, with creative solutions or they get tricky, a lot of times it's just knowing math, right? I mean, and it's kind of unfortunate, but that's really what it boils down to. Like if somebody gives you, you have an array and all the numbers are sequential, and one of them's duplicated, how do you find the other one? Well, you're probably, as a programmer, you're like, well, I'll loop through it and find the one that shows up twice, right? Well, now you're in O(n) time. But if you were to just sum the entire, well, I mean, I guess you're still in OM time, but there's a way to where you don't have to scan it twice and have extra storage. And you can basically, there's an equation to where, and I've got a link that actually came out of, oh my God, what's the name of this? The Imposter's Handbook. That's a YouTube link to a guy named Numberphile. But there are equations to where you can, if you know the beginning and the end of a sequence, there's an equation you plug in that will give you the sum of the entire thing. And then all you have to do is take that minus the diff of what you expected, and you've got your number, right? And so that's very fast time for what you probably would have in your programmer mind said, well, I'll just loop through it and do this thing, right?
Yeah, I was actually given one of these as a question one time, and it totally threw me off because I didn't recognize it for being a constant time, because like why would I, right? But the way the question was worded was, you have an array of unknown size of integers that are not sorted, so they're not in order, and but they are all unique integers, and they all start at, I want to say, if I remember, I don't remember if it was 0 or 1. I'm pretty sure it started at 1, right? The array started at 1, and they're all, let me say how to say this. If you were to sort them, they would all be contiguous, except there's one missing one, and you got to find the missing integer, right, out of that list. And I didn't recognize that, oh yeah, there's a math formula for that, because you kind of already have an idea as to what the max integer is based off of the size of the array. Right. So yeah, there was a formula for that. And I'm like, oh man.
Yeah. I mean, going back to this, what Joe said, this is so important. Like if you're in an interview with one of the big tech companies out there, these are the types of questions that they ask because they want to see how you think through things. Right. And if there's a mathematical approach, it's probably worth asking the interviewer, hey, is there some sort of formula I can use? Right? Is there a mathematical equation I'm just not aware of to do this? And a lot of times they'll, if they see that you thought in that realm, they'll help you out and be like, okay, well, just assume you can call this function called, get value, right? And that they might go with that because, like Joe said, a lot of times these things are way more complex, and it's not like you're just gonna be able to pop this formula off the top of your head,
Yeah, one example I really like is trying to find prime numbers. Like if I ask you, hey, find me the 2 millionth prime number, then kind of a naive approach is to say, well, I'm going to loop from 1 to 2 million, and I'm going to check if each number is prime, which means checking if it can be divided by any number less than it. So you can think that's n squared algorithm. Like we're going to loop until in this case, it's not an input size. We're actually specifying like a limit, but it operates the same way. So, go to your input size and check each number less than it's n squared algorithm. It performs horribly, and you're not going to make it to that 2 millionth number in a reasonable amount of time. But if you start thinking, well, you know what? If I want to know if the number 5, or we'll say 10, make it interesting. If the number 10 is interesting, or if the number 10 is prime, I don't need to check if it's divisible by 9 because that's going to be covered by a smaller number. I only need to check numbers that are half of it or smaller. But then you're going to do that. But what we kind of talked about tonight is like dividing in half doesn't change your runtime. So we're going to be multiplying n for the outer loop times n divided by 2. That's still an O(n) squared algorithm. So even though you're halving the operations you're going to do, you're still not going to find that 2 millionth prime in hours. You're going to have to run that thing all night. So the solution here, I don't want to spoiler, is it gets a lot more complicated if you try to write your own prime number generator, but you only have to look up to the greatest common divisor. And you can even do that by keeping track of all the primes as you go along, which in this case would be 2 million. So your space complexity is not going to be so great, but you can basically look at the prime numbers up to the GCD and reduce that. And so the net result is that you're going to end up running in I believe it's n log n time for a good prime number generator. And there's different techniques and different ways to get that even better and whatever, but it's just kind of a cool way of seeing this kind of in practice where the obvious solution is terrible. And as you whittle it down, even things that seem like it'd be really good, like dividing in half, like you would think would make a huge impact, still going to run all night. It's not until you really like pare this down into a small logarithmic or even like a square root type solution or set of data to look at, that you're going to see some real benefits.
And so what you were saying, though, is you're trading off the time complexity for the space complexity. In this
Yeah,
case.
in that case where you're memorizing, that's actually a really common technique in some code words problems and things like Project Euler, where you absolutely do make the trade-off and say, you know what, I can store 1 million numbers in RAM, no problem, but I can't recompute 1 million prime numbers from scratch every time.
Right.
So just to wrap up here on n log n, I don't know if this was said, but I wanted to make it clear that when we say n log n, that's n times the log of n.
Yeah, and that's what I kind of screwed up on last time when we were like, well, that could get less than, and no, for the most part, n log n is going to be greater than, or no, it will be greater than n and less than n squared. So, all right, who's got next?
Let's get into the really bad ones now. This is where you have a very bad hockey stick on the graph. O of 2 to the n. So we're flipping the equation.
Yep, and just kind of give you some perspective here. For the example of 1,000 where constant time was 1 second, linear was 1,000. In this case, 1,000 input is, I can't even tell you how much it is. It's like 3 with 200, I don't know, it's billions of years. It's longer, much older than the universe. Like there's not even names for how big this number is.
Well, you've got 3 to the 284th. So scientific notation, basically 3 with a decimal spot that should move 284 places to the right billion years. So it's more than 3 Googles.
Oh, way more than Google. Yeah. Yeah.
That's ridiculous. Or 300.
Does that make it an Amazon or an Apple?
It's like,
or is it an Amazon plus an Apple?
300 Google billion years. That's about what it sounds like.
Yeah, and I think I might have messed up a little bit. I think I should not have that billion in there. I think it should just be 3 with 284 zeros years.
Oh, okay. Oh, yeah. Okay, so 300 Googles years.
Yeah, but it's kind of like insignificant when you're like, a billion's what, like 8 more? Like, who cares? At 284 zeros, like, ugh.
Oh, man.
So, I was trying to find like examples of where we might be tempted to run into an O of 2 to the n type of problem. And I was really having some trouble, but I did find this one answer from Stack Overflow where the author of the answer suggested that algorithms running in O of 2 to the n are often recursive algorithms that solve a problem of size n by recursively solving 2 smaller problems of size n minus 1.
So things that keep going down and calling themselves, or calling things that keep splitting it up.
Yeah, so then that led me into thinking like, well, would we be talking about like, because even in we mentioned the Imposter's Handbook, right? He mentions in another chapter that was after Big O about, hey, here's a bad way to solve Fibonacci sequence, right? And he does this type of thing where it's like, hey, Joe said, hey, solve to the 2 millionth prime number. Well, what if you were to be given a question of like, hey, solve to the 100th Fibonacci sequence, right? And the first iteration he was going is like, well, you take that 100 in and you would, recursively go back, 100 minus 1 and 100 minus 2. And then each one of those would recursively go back, 99 minus 1 and 99 minus 2. And then 98 minus 1 and 90. So he drew out this graph of it, right? And he was like, he worked with much smaller numbers than 100. I probably should have stick with something smaller. And you could see that like the point that he was showing in the diagram though was that like, look at how many times the same function with the same argument gets called in that regard, right? And he didn't call it out specifically as O of 2 to the n. So that's why I was like getting kind of thrown in my own head. Like, I think this is 2 of O to the n.
It sounds based on the description like you're doing something twice, running 2 smaller ones that both do something in n operations. Yeah, I mean, I don't know if that's true or not, but it sounds right.
I mean, the thing is, when you see this kind of stuff was when people try and break up problems into super modular type
Oh
solutions.
yeah.
Like you see this kind of stuff with SQL queries and that kind of thing. You try and make SQL modular, and you start running into this kind of garbage where you keep calling the same methods over and over to get the same results back. X number of times, and this is where you see it typically is when people try and get clever with using the least amount of code to yield the most results.
Yep, which is unfortunate.
Is the answer.
Sometimes.
And I came up with a little contrived example here where I literally tried to do something that happened in 2 to the n operation. So I came up with a little function where you pass like an exponent, and it will give you a buffer, a binary buffer back with 2 to the exponent number of zeros. So if you give me a 5 to my function, I'll give you a binary array of zeros of size 32. And so it's really contrived, but it was just kind of funny that I would print it out in like Chrome. I just did it in JavaScript in the console. It's just funny to kind of put 100 in there and see it like start spinning for days.
Awesome.
All right. So I think we said this, but just to be clear, right?
This is in the yellow.
This is in the this is in the bright red.
Yes.
This is very red on the Big O cheat sheet. So if you find yourself, maybe here's the tip then. If you find yourself doing recursion, number one, that should already be a red flag in terms of space, right? Of stack space. You need to be aware of what size inputs you're working in. But if you are doing anything with recursion where you're just iteratively going back over the same collection, maybe that's the sign that you might be in this territory.
Yeah.
Maybe.
I don't know. I don't know that I've ever really seen one of these guys out in the wild. Like I think you'd have to try to mess this up so hard.
Or if you sat there at your computer getting old while this thing was still trying to run.
Yeah.
That might be the other one. I mean, we did say 300 Google years. So, if after Google years you're still sitting there waiting on it, you've probably done something wrong.
And you still got years and Apple years. So you got time.
Yes, you got that.
Well, there is one worse thing that we typically talk about. This is the worst one that we typically talk about, which is the n factorial. And unlike the exponent, this one is actually something that does come up pretty often. In fact, every time we try to get permutations of an array, so our 5 array example there, it means we want to see 1, 2, 3, 4, 1, 3, 2, 4, 1, 5, 2. Every combination that's possible with that inputs, that's an n factorial operation. And so this is the one where I figured this out for our size of 1,000, where 1 took 1 second, 1,000 takes, I'm not even going to try, I didn't even write down the first number because it matters so little. It's over 2,500 digits. 2,500 digits of seconds.
That's a lot.
Yeah, I took it into Visual Studio Code just to kind of so I could even count like the number of zeros. I had to do a little funky math to even figure it out, and it was like crashing code on me even to like get all that stuff on one line so I could get the length of it.
So I want you to picture in your head, like when we go back to the Big O cheat sheet for this one is so bright red, it's on fire. Okay. And when we talk about a hockey stick, what I want you to imagine is you draw your normal XY graph, right? Picture that in your head. Now go from 0 and maybe think about drawing a curve, but then instead change your mind, just go straight line up, right? That's pretty much O of n factorial, what this does.
Yeah, there's no good at all.
Yeah, I actually, have you guys ever been in a situation where you've had O of n factorial problems?
I don't think so.
Oh, I've done a little bit of stuff like toy problems and like something like Code Wars or whatever with factorials or.
No, I mean like where you've been real world given.
Oh, no.
See, this is where, you remember how Rob Connery, the author of the Imposter's Handbook, right? He told this story about like how he didn't recognize, he actually lost a job one time because he didn't recognize the problem and couldn't, because he didn't recognize it and know how to say it to someone else, then it ended up later costing him a job, right? And I might have mentioned this before in a past episode, but it definitely, like, while you guys were talking, made me think about this, where like I actually had this come up one time where it was what the customer was asking for me or asking of me was an O of n factorial problem. But at the time, I didn't know how to communicate that to them. But all I could say is like, look, what you're asking for is not possible in my lifetime. And the best I could do would be like, look, I'm going to go ahead and write some code to do it. And then we'll take some time samples and I'll show you how this is never going to finish in a reasonable amount of time, and that was as good as I could do. And so that's why it's important to try to learn these things and understand these things. Cause when we talk about these, like you were mentioning the 2,500 plus digits, right? If we take Jeff Atwood's example here, where each unit of time was 1 millisecond of time, right? For n factorial, where n is 16, it's 663 years.
Using milliseconds.
Mm-hmm. It would take 663 years. So that's the trouble that, like, young me, I want to go back and kick, young me in the butt, because it's like, I didn't know of a good way to communicate that to the customer. Like, hey, this is not possible, right? This isn't going to finish. This can't be done in my lifetime. So, I don't, and of course someone else is like, no, I can do that. It can be done.
Of course, not a developer never ever tried to step on somebody else and say, yeah, I can do that.
Oh yeah. Well, to your point, not to pick, but it was a project manager. It was like, no, that can absolutely be done. Yeah. I'm positive that can be done.
So here's the thing, right? If you start going around talking like, well, that's O of N, then you're probably going to get looked at with stinky looks all over the place, right? Like, and Rob even says in his book that the problem is it makes a lot of people very uncomfortable. If you don't have that computer science background and you haven't gone through all this kind of stuff, a lot of times it does make you uncomfortable because you'll want to step out of it. Like I didn't actually go to school for CS specifically. I went for CIS because I'd already been programming for a long time. And I was like, well, I want to get the business side of things. And so like DiffyQ and that kind of stuff that Joe probably struggled through, and I think you probably did too. It's one of those things that you kind of miss some of these. And so if you don't have that heavy background, it's can be intimidating, right? But hopefully listening to what we're talking about here is we're trying to put it in plain language, right? Like ON is something you can look at and see, right? ON squared is, you think of just the loop constructs and all that stuff. You should be able to kind of look at it and say, hey, I think that this is probably ON or this is ON squared or whatever. Like it should be a language that you'll be able to communicate. So like that situation you're talking about, you could have looked at the guy and been like, that's ON factorial.
Right.
Can't do it.
I mean, even I look at now that the way we are armed with information, right?
Yeah.
The Big O cheat sheet is an invaluable resource, right? Because you can just visually show somebody like, hey, here it is. This article from Jeff Atwood, right, where he has the table, invaluable, because you can immediately just put it in front of somebody's face and be like, look, this is why what you're asking can't be done.
Right. I'm not speculating. I'm giving you evidence.
Yes, exactly.
Right.
Yeah, and I don't think we ever actually said what a factorial is, did we?
I don't think we did, but isn't that the thing that everybody remembers from primary school?
I always get it mixed up with summation, but it's the product of the integer and all the integers below it. So, if our example input of 5, it's 5 times 4 times 3 times 2 times 1, which you can obviously is going to be much bigger than just 5 times 5, which is n squared.
Yeah, it gets huge fast.
Yeah.
This is the way I want my pay scale to work. What do I got to do to make that happen?
I would like a 6 factorial raise, please.
Yes.
I found a calculator online that will list permutations. I was like, is it really that many? It doesn't seem like that many. And so, it kind of like you tell it how many you want and it'll generate all the outputs for you. So the first one I did was like 1, or no, not 1, like 5, I think. I was like, okay, here's a ton. I'm like scrolling. I'm like, all right, well, I don't trust this. It can't be that bad. Let me try 10. The website's just like, no, that's too big. Like,
Yeah, I can't do that.
it's like I can't permute 10 items in an array. That's going to be over 3 million. It's going to crash your browser, bro.
Wow.
That's crazy. So yes, as you said, that one's very red. That's on fire red.
Yes,
blowtorch type of red.
Yeah, your computer just melted and you're out of a job.
Very nice.
Yeah, you're not going to make it to Patch Tuesday before that thing quits.
That's Tuesday. For Windows Server 2 billion.
Right.
Yep.
Oh man.
All right. So we will have a lot of links in the resources we like section for this episode. So if you're listening along, you can use your podcast player can usually list out the show notes pretty well.
Yeah, most of them
reasonably
do.
well.
The Google podcast player doesn't. I mean, it's very small, minimal. Maybe it's a different feed that it's coming from, but we need to take a look at that. But for most of them, you'll be able to click on the links and go look at these things.
Yeah.
Yeah, and we've been slacking on the videos, by the way. We've gotten a lot of feedback about it, and those are coming back. I've just been slacking. If you see this video right now, you can see that my office is a mess. I just moved, and I'm still picking up the pieces of my shattered life.
Yeah, I need to get the other one back up. But yeah, we're getting them back up. We got.
He sounds so sad. Picking up the pieces of his shattered life. Come on, Joe.
That's a song, isn't it?
Come on. It's not that.
That's a song.
Cut my life into pieces.
This is my last resort.
I'm so sick of moving.
Awesome.
Just one more time back to Atlanta, and then you're done.
Hey,
All right.
and by the way, we keep forgetting we also have a codingblocks.net/resources page to where if you go up there and check it out, we have like our favorite of our favorite resources up there. So every show notes page will have the resources we talked about on that page, but like our very favorites, the best of the best, whatever, are on that resources page.
Including a referral link to Pluralsight, which has amazing videos on algorithmics. That's what they call it.
You know what else? Hey, by the way, here lately, I've been watching a lot of LinkedIn learning stuff, man, which used to be lynda.com, right? They bought it. Man, they've got some good stuff up there too. So I highly recommend that. I probably should get a link up there too, because there's some really good courses up there.
Yeah. So as one famous Coding Blocks host would say, check it out.
Check it out. All right.
I think that's going to become the catchphrase for a while now. Check it out.
It reminds me of chicka chicka.
All right. So let's get into Alan's favorite portion of the show. It's the tip of the week.
Yeah, baby.
All right. So this was emailed to us by Joe Reedley. I hope I'm pronouncing that correctly.
If not, we've said it wrong so many times.
Oh, have we mentioned him before?
Are you kidding me? Joe Recursion Joe?
Joe Recursion Joe.
Oh, I didn't recognize that.
We can usually say that properly.
I didn't recognize that was him when I saw it. Dang. No. I'm sorry, Joe. I didn't put two and two together. Math is hard. So he sent us, because I've had like this affair with Python going on for a while now. So you have a full Python IDE for iOS with an app called Pythonista. So I have links to it. I haven't had a chance to try it yet. It's like high on my list, though. I want to try it out. It looks so cool. But I think part of what I'm struggling with, though, too, is that, like, what's my use case for writing code on my phone or on my iPad other than, like, I'm on a train and, I'm bored, right?
Right, yeah.
Because at first I was like, oh, yeah, that'd be cool. Code Wars on the go. But then I was like, well, I guess I could just go to codewars.com then.
Yeah, but typing on a phone just stinks.
Well, it's got type ahead, though.
How many times that bit you? Never?
I mean, yeah, well, I'm not speaking from experience, so I can't say. But, like, looking at the pictures, though, they show you where, it's pretty smart about what it's I'm trying to, like, type this while I talk, and that's hard.
So you're messing with it right now? So.
No, like I said, I haven't. That's the one thing. The app is $10, and that's another part of the reason why I was like, man, I'm too cheap, because I won't spend $10 on this app until I can think of like a good use for it. And I'm like, I just got to go ahead and get it. So I'm gonna go ahead and get it.
Yeah.
But
yeah, you should buy it. That's the thing, man. Really, iOS
here's
needs
what I'm talking about. Code completion.
A try until you buy.
Can you see that?
Yeah, sort of.
Sort of. How about, can I get it closer?
Kind of furry. No, not that great.
None of that worked?
No.
Dang, I failed.
All right. So coding on iOS, his tip. Mine, I got lazy this time. I guess I got lazy, or I just want to give some people some credit in the Slack group. So Super Good Dave, he's been on several of our community talks. He actually came back with, I don't remember what episode it was. We were talking about the faking framework that was created to where it created like people.
Oh, wasn't that last episode?
Was it last? I can't remember, man. My brain's going. So he mentioned that there's tons of other ones out there already as well. So there's Ruby Gems. There's a faker that's called that can go create a ton of stuff. There's another one that's also a Ruby one called Factory Girl, and it will make a bunch of fake data. There's another one that allows you to specify the data you want to download as a CSV or JSON or whatever, and that's called Mockaroo.com. And then there is a faker in JS that Vlad.os gave us, which is it's on NPM, and it's called Faker, and it will also generate fake data. So there's stuff on all kinds of platforms, JavaScript, Ruby, etc., an API one. So go check those out. The links will be in the show notes, and thank you for the tip, Dave.
Yeah, some people are so creative with the names. VladOS, Joe Recursion Joe.
Vlados. You guys play Portal 2 or Portal 1?
Probably own it.
It's been a while.
Probably don't play it.
It's awesome.
I played it. But
GLaDOS.
God of War, man. God of War. That's what you got to play.
That was the voice, though, in the Portal games, right?
The computer. Oh, you guys are embarrassing me. You need to go play Portal 1 and 2 right now. They hold up very well.
Oh, come on, man.
There's your tip.
I got a whole closet full of games I don't play.
Portal is fun, but something about the motion eventually gets to me.
Really?
Yeah.
Emotion or motion?
Motion.
Okay.
Like some of those maps will get me like sick after a while.
You just got to fortify and push through.
Apparently.
All right.
Treeform.
I'll play.
I guess
one day.
All right. Well, speaking.
Hey, you don't have your tips in here. We're skipping, Joe.
No, I just came up with it now. I haven't typed it in.
He's being secretive.
That's right.
So I don't think that I mentioned, or I don't think that I've suggested that you check out dev.to. It's recently went open source. It's kind of like a blog aggregation tool, except the content is actually there. It's not like a Reddit or a Hacker News where you actually like kind of click off and go. But it's got a really nice community, which I think is really important. It's really active. And the site's open source now. It's really cool. And you can see what's coming. They've got a great roadmap. They're doing a lot of work. Super Good Dave, you just mentioned, has actually been blogging there, writing a lot about Vue recently and doing kind of like a JavaScript Type 30 thing. Dance to Die, Goprogman, like a lot of the people that we talk about and really like to follow are all there. And so if you hit me up on Dev2 or anywhere, I can give you a list of really awesome people to check out there. And if you're a blogger or thinking about blogging, one thing that's really important to note is that you can blog on your own blog, say like joezack.com. I can blog there and then sync the content to dev.to. And when I do that, in order to not lose my Google juice, you can set the canonical reference. In fact, it's already kind of preset if you do the sync back to your original blog. So long tail, 5 years from now when people search the thing you wrote about, they're still linking to your blog. But short term, you're finding tons of readers that you would never have found otherwise who are just browsing and hanging out on dev.to because it's an awesome site.
Man, look at you throwing out marketing terms on our coding podcast. Long tail.
Right.
People are like, what?
I've been doing some reading.
What is he talking about?
So you got to check out the site. It's dev.to. And actually, you should follow them on Twitter and follow everything they're doing. Just because they're doing really cool stuff in the programming community and making life better for developers and content producers, which is fantastic. And it's really nice and positive. Not to compare it to other communities that aren't so much those things sometimes, but it's really great. You should check it out. Dev.to.
Check it out.
Check it out.
All right. So with that, we ask if you're listening to this, maybe a friend has shown you the way, and now you're hooked. So go on to iTunes, Stitcher, or more using your favorite podcast app and subscribe. If you haven't already left us a review, we would greatly appreciate it. I'm not lying when I say it puts a smile on our face. So you can find some helpful links by heading to www.codingblocks.net/review.
And while you're up there, you can check out all the show notes, examples, discussions, and more.
And send your feedback, questions, and rants to the Slack channel, codingblocks.slack.com, and make sure to follow us on Twitter at codingblocks, and head over to codingblocks.net. You can find all our social links at the top of the page. Also, just want to stick this in there at the end. For the Horde.